My introduction, Devanshu Shrivastava from first PEM. So basically, the reason why I choose PEM, I should mention that also. What happens when you just, sorry for the analogy, it can go somewhere else, but let me try. When you find someone attractive, what you do is just try to approach them, and your friends help him or her to approach you. So just for me, the physics is that thing that interests me. That friend is the math that will help me to get there, and electronics because I hate it. So let's come to the topic. My topic is the stellar evolution, as you can see. So what happens? See the human nature. Human nature is so peculiar. Sorry, can I use one sentence in Hindi? What happens? जो इंसान है उसको दूसरों की जिंदगी देखने में बड़ा मजा आता है. So that's exactly what stellar evolution is. We see how a star gets birth, goes to its life and then death. So that is the stellar evolution. We have last week and I will go further. Okay, so first see you have a gas cloud. Okay. As you are in Bangalore, you are familiar with clouds. Bangalore is always cloudy. You have clouds in here also, but that do not react, it's not from stars. Okay. So there you have small clouds, but think of the biggest number you can think. I would like to ask my friend, please fill the biggest number you can think. Any number.
8904826113.
Okay, just into 10 to the power 15 or something. This is the radius, then you draw a circle or square with that radius. Now you think the cloud and the dust and every particle is inside that area. So you think how much big cloud we have. So we have something called genes instability. It states that not the genes of the denim genes, it is the name of the scientist. His name is, I guess, James Jeans. He was a British physicist. So he predicted that amount of the mass of which you will get the instability, genes instability. That means when this is the point where the clouds start showing the behavior that is not normal to us. That is unstable cloud. Okay, so that is genes instability, and we have genes mass. The formula is written over here. Genes mass is that mass for the radius r that we need for stability of the genes instability. Okay, as I mentioned, the cloud. Okay, that cloud is called molecular cloud, or you can also call it stellar nursery, given that in that region of the cloud star formation is going on. Unless and until star formation is not going, you cannot say that it is a stellar nursery. Fine. So molecular clouds are of types like small molecular clouds, giant molecular clouds, and one more is there, I guess, high altitude molecular clouds, something like that. But the latter two, small, and the third one is not of our interest. Our interest is giant molecular cloud. So in giant molecular clouds, I have a few data like I mentioned. Yeah. The size of the giant molecular cloud is 10 to the power 3, goes to 10 to the power 7 solar mass. That is the size, like the mass in that area. We have such big cloud. Under that cloud, we have dust particles with ions, electrons, helium, and hydrogen, and everything. So what happens? The genes instability starts to come into picture. Genes instability do what? Okay, so one thing that I would like to mention, what happens? We do not yet know how that I would like to mention that we do not yet know how that cloud forms those fragment parts. Like, see, you have cloud particles here, here, here that are randomly scattered. But as soon as genes instability came into picture, they divide into something called fragments. Like you have particles here, then you have particles here, like this. Okay, so they are not so randomly distributed, although they are randomly, but when you look into the bigger picture, they are not that randomly distributed, they are just like a fragment. So in this, we have something called dense region. That dense region is called clump. Okay, so if you have a good amount of matter in a given area, that is with a good density, that is called clump of that particular cloud. If you have so many clumps in that area, and there is some reason where the clumps are also together and they form a bigger clump, that is called the core of that cloud. Okay, so basically in that is the star formation begins. How that begins, that is about next. Okay. First stage is called protostar. First, this idea was suggested by called Shushiro Hayashi. I cannot pronounce that name. I am very good, but okay, leave it there. But we have something called protostar. So in protostar, what happens? You have the core of the cloud. There, these particles are just contracting, compressing in their own way. Think like you have a big cloud that is just coming to a single point. Like here is the point, particles are all around it, they all are coming to a single point, every particle in this particular region. Okay, so in that case what happens, gravitational pressure increases. As soon as we come close to the given region, gravitational energy converts to heat and then we got radiation. But the good part here is, we need to maintain an equilibrium between the radiation pressure and gravitational pressure that is creating there. Otherwise, if you, one more analogy I would like to present. Gravity is exactly like that, sorry for this thing, but the gravity is exactly like that older person of a family who tries to connect every person of the family. Like again, if everybody understands Hindi here, I'm sorry, I'm just more familiar with Hindi. Can I use Hindi? Okay. So imagine we have a family, there is a one older person, like we can say grandpa or something. तो वो क्या करते हैं? He is like every family member, हर एक family member को वो कोशिश करेंगे कि मतलब सब साथ में रहें, परिवार ना बिगड़े. That is the work of the gravity. But we as a youth, what we do, we behave like a cat. नहीं हमें तो बाहर जाना है, हम तो अपनी जिंदगी जिएंगे like that. But equilibrium is necessary in that portion. Otherwise, you will not get your goal. And even if that older person, if he tries so much to compress you, if he tries so much to bond with the family, you will start hitting. So the basically point is equilibrium necessary in everyone, even in your family and everywhere. How will you write that equation of the equilibrium? I have an equation. Should I mention the equation also in the question? That is called hydrostatic equilibrium. You have 4 pi r square r which is balanced by g 4 pi r square. This is the equation which values the this is called hydrostatic equilibrium. This is the equation that manages the gravitational pressure and the radiation pressure. So once that pressure is managed, then what happens? The start, it's a nuclear fusion start. For the nuclear fusion start, you must have something called I'm not getting that term, but you have particular temperature. Like until unless you reach that temperature, you cannot get nuclear fusion. But that doesn't mean radiation will not come from that area. Okay. Radiation is not mean from nuclear fusion. Nuclear fusion is mean from just the energy source for the star. As soon as the nuclear fusion starts in the core of the cloud, you can say the star is born. When the star is born, the initial phase, during that, okay, the nuclear fusion starts, but even though nuclear fusion starts, the clouds here, they also come to this part. They do not rest, like they come to this part, they compress. Now think, radiation pressure is increasing as the nuclear fusion increases. Okay. Then why these clouds come this side, where they do not go outside? Like you are getting more radiation, they should go there. Okay. What happens there? There comes in role the molecule H2. The good thing of the molecule H2 that works as cooling agent. If you have good amount of H2 in this cloud, they will absorb the radiation and they will emit in 28 μ. So they radiate energy through this. Thus, you do not worry about that heat pressure. The cloud comes there. So this part is called protostar, the initial process where the falling matter falling is still going on. That doesn't stop. That's called the protostar. Then we have something called collapse of protostar with this. This I mentioned, if the nuclear fusion starts. Now think, if we do not have sufficient mass, we do not have sufficient temperature, then the cloud is there, the core is completed. We have core, we have cloud around it. Now what? Do we call it a star? Because the nuclear fusion is not there. I said to call something a star, you must have nuclear fusion in the core. This does not have nuclear fusion. It has cloud like something called disk and something. This is called failed star. And in scientific word we call it a brown dwarf. So I also have some data about brown dwarf I would like to mention. Okay. So, yeah, this is, if you can see everybody, this small dot, this is a brown dwarf. Okay, so brown rock doesn't mean they are only of the brown color. Although they do not have many brown rock are not in the visible wavelength, but they do get wavelength from that. This is the bigger star. This is the brown rock. So like our Earth get what to say visible. This can also be visible. So they are in many colors like magenta, blue and all. Brown rock is just a name given to it because if you do not have any star near it, it will be not in that visible. Okay, the first theory of brown rock was suggested by Indian scientist. This is Shiv S. Kumar in 1960s. We have some statistics to leave that part because we do not have much time, so I should leave it. Okay, pre-main sequence. I mentioned, go to the protostar side. I mentioned the falling of the matter is still going on in the protostar. Nuclear fusion has been started. Now what? That part where the nuclear fusion starts and the falling is also going on, that is called pre-main sequence. As soon as the equilibrium starts, like you say, you do not have much matter around it to get into this core. So when that portion comes, that is called main sequence. Okay, our star is in mid-age of the main sequence star, and pre-main sequence, main sequence are just, see, the problem is here is we have so much categorization. Main sequence is a bigger picture. You divide it to pre-main sequence, the main sequence, and post-main sequence. Combine it together, it will become the same picture. Okay, so we have this something called the HR diagram. There was two scientists, sorry. So what they do, I think in the Harvard University, there was a group of scientists. They collected data from so many clusters. They managed it, they arranged it so like that you get absolute magnitude and all. These scientists independently used their data, and plotted a graph. That graph was something like this. If you plot, okay. Depending this, if anybody can see. If that star in this graph comes somewhere this line, then that is white dwarf. White dwarf I will mention later. This side is called the main sequence. I will not go to the pre-main sequence and post-main sequence. And these are all other, like go to the supergiants and giants and all. We have two type of what to call thing through which nuclear fusion goes. That's for PP chain and CNO cycle. I will not mention that also. Okay, so this is the funny part and the best part that I like. Some scientists called Russell-Boget theorem. Sorry, I'm not good with the English pronunciation much. So it states that the mass and the chemical composition are two important parameters that decide a star's fate. If you all guys can relate it to something else, just relate it. The theorem is named after two scientists called Heinrich Boget, I think, and other is the Henry Norris Russell. So this, see, in Hindi we have a sentence called "Poot ke pav palla mein dikh jate." That means if you have a child in something called I don't know, when a child is small, the behavior of the child, the reaction and the thing that the interest that show towards the thing, he suggests that how and what he will be in the future. Like this is Hindi saying in my video that I am stating. "Poot ke pav palla mein dikh jate." In the same manner, what happens in the star case also. You just know the mass of the cloud, you can predict what will happen to it and how it will develop. You know the chemical composition, like if it goes to the what is called iron, till iron, if the fusion goes to iron, so you know how it will end. So this is basically human. There is a formula and equation and all. I'll skip that part. Okay, so there is something called white dwarf. What are white dwarf? They are the actually mostly interesting thing. Okay, I forgot the name of that star, but what happens in somewhere early 90s, there was a scientist, he was looking at the stars in the sky. So what happened, he suddenly got a peak. So in earlier days what happens, if you get something interesting, you know what people used to say is like, there is a ghost, there is an alien signal and all. I will mention one more story of the alien signal when I come later. So he just looked at the sky, he was doing some survey. He got a peak in the spectroscopy. He, in whatever, what is that, spectrocalorimeters, no, I am not getting that name of the device. he was doing through that. So he got a peek. He thought there is something disturbances, some ghost came passes by nearby and all that. But later, more scientists did the same observation, and they got to know that there is something. There is something that is compact, that is dense. So the further you cannot see. So they started doing more analysis. One small dot is here. This is Sirius A, this is Sirius B. So this is a white dwarf star. So white dwarf stars, what happens in white dwarf stars? You see, I'll explain of the sun part. You have a core. Fusion goes on here. Sorry, is there something? Is there something? No. So you have a core. Okay, fusion is going on here. But what if the fusion stops? You get out of fuel. Then what happens? You have no gravity to control the radiation pressure. The gravity parts immediately invisible or say vanishes. Now the radiation pressure come into picture. Slowly and slowly, I'm talking about small mass white dwarf. Okay. So in what happens? The radiation will slowly evaporate the outer layer. Okay, it will evaporate, like it will radiate out. So if you draw graph, log P, this is R. So I think it comes something like this. This part is called core and this is envelope. So radiation, the radius increase, like it will go here, then here. So radius is increasing basically. Okay. So this happens in case of small mass white dwarf. The outer envelope reduce, but if the mass is good enough, then it can create something called planetary nebula. Okay, this is I'll skip that planetary nebula part. So okay, when this evaporates, this creates a beautiful scene. You might have seen the planetary nebula's picture. So it creates a planetary nebula, and what left behind is a core, because the envelope is radiated. So what we have is the core only here. That core is called white dwarf star. Okay, so now you see if you have a good mass in the core. Okay, so the gravity is still compressing it because you have matter in it. Matter in the core is not radiated. Matter is here. Now what happens? You get something called degenerate matter. Here, electron degenerating pressure comes into account. You know, a fermion of mass m and half spin cannot have same quantum state. Okay. So in that sense, when you have electrons, I am talking about free electrons. You have electrons here. When you will just compress it, the electrons do not allow them to fuse or to come closer. So, you got electron degeneracy pressure. That electron degeneracy pressure overcomes the gravity again, and you cannot just react this electron together. Okay. So you got a stable core here. That is called white dwarf. Now, I forgot to mention one thing. What is the limit to get the white dwarf? Okay. Sorry, let me say. The mass of the core should be less than Chandrasekhara limit. Okay. It will be like 1.44 solar mass, less than that. If you have the core mass of this amount, then you will have a white dwarf. Okay. So now what happens? We come to the in the massive white dwarf, you can also get a supernova of type A1 if it is massive enough to create that blast. Okay. Other thing is what comes to the neutron star. Now think, what if the mass of that core goes above the Chandrasekhara limit? What will happen then? Same thing happens, just add something else. If you compress it more, okay. Neutron stars are massive than white dwarf, everyone know this. So if it is massive enough, then gravity will be more. If gravity is more, then it will compress more. If it will compress more, what happens? The proton present here will react or will come together with electron and will form something called neutron. As soon as you get neutron here, enough neutron to overcome again the gravity, then you call it a neutron star. So one interesting thing about neutron star is the same thing occurs with the first also. You have envelope there that also blast, that also creates supernova, but that supernova is more energetic than supernova of the white dwarf. That is called type 2A supernova, I think. So okay. Type 2 is supernova, that is, now you have a neutron here that is called neutron degeneracy pressure, that will again overcome the gravity. Now again you have a stable core here. So neutron star, what happens, they spin so fast, like you can get, there is one neutron star in the Crab nebula, spin of that is 0.033, I think, or 0.33 second. So they spin so fast, like the period of the spin is that one. Okay, then I was telling about an interesting story about the aliens. So what happened, there was a scientist, girl scientist, actually she was a PhD student. So she was again doing some PhD research. She looked into the sky and she got a peak. Okay, while she focused her telescope to somewhere in the part, she got a big peak, like in his telescope. So she thought that some alien is sending message to the Earth. They also named it. They called it, I think, Little Green Man. Yeah, that was the name. I think they nicknamed that analogy. Later, what more scientists, as soon as you take the name of the alien, I'm going to came into interest. So more scientists come into picture, they analyze the same thing. Then later, today we have something about 200 pulsars absorbed in our universe. So one more interesting thing about neutron stars is that they have a good magnetic field. Like I think the order is 10 to the power 12 or 18 watts. I'm not sure about that, but that big you have. So as I suggested one analogy, that you get a type 2A supernova. So if you look at this to bigger picture, you will get remnant here, like in Crab nebula. You get remnant here. But in most of the supernova remnant, I think in only 72 we have that remnant, not in all of them. So when you look into this, you will not get that remnant in the neutron star. So one more telescope is coming, that is called, I think, SK. When that telescope comes, we can see if that analogy is true or not. The limit of that is up to 3 solar mass, again to the Chandrasekhar limits. Okay, so I have one blank here that represents basically black hole. Okay, so if projector would have worked, that could go good. We have something called black hole. Now, if the core mass is more than 3 solar mass, then there is something called, I think, Schwarzschild matrix. When you solve it for the radius r, and if that radius is below the name of the science is what, Schwarzschild, whatever, if you get that below that, and I think that is 2gm5 something like that. Yeah, if you get below this, then you get a black hole there. I will not mention black hole more. What is it? Yeah, 15 minutes. You have 15 minutes more. Okay, so now this is the basic model of how stellar evolution goes on. You have something called stellar nebula, like I mentioned that stellar nebula and nebula and molecular clouds. You get into protostar. Then, depending on the mass of the protostar, you get to know how it will react in future. You have a small, if the planetary nebula, sorry, if the protostar is not massive enough to go to big star and medium star and all this, you go to a small star. Very small star, medium star, big star. So this is basically the model. So in big star, you get, okay, one more. Big star are massive enough, name suggests that. You have good amount of matter, good amount of information go there, you have good amount of energy. So they appears to be blue because they are hotter. Then it goes to red supergiant phase. Red supergiant phase is exactly that phase I mentioned. The envelope and the radius increases. That is called supergiant phase. Then you got supernova remnant, and after supernova remnant, we will get neutron star or black hole. That depends on the mass of the core. If you have medium-sized star, the medium-sized star goes to yellow dwarf. Again, why yellow dwarf? You know, because it do not have enough matter. It do not have enough fusion to get into that temperature in the latter part of his life. Then you have red giant, it goes to planetary nebula, I mentioned as here, then white dwarf. Okay, the white dwarf can also go to black dwarf. White dwarf is actually, a few scientists call it what is called a retired star. White dwarf, what happens? You have this core, it will emit till few time, means few million or billion years. After that, it will stop emitting light. It will go off in the darkness. Like you will have only a core part, no light. Okay, just next one. So,
do stars act as black bodies in any of their?
sorry.
Do stars act as black bodies from birth to death any stage, in any stage of
Stars actually are the black body radiation. You see what is black body radiation? Black body
Are they black bodies? Perfect black bodies.
There is no ideal black body.
Stars, all stars.
You cannot say about round rock actually.
Yeah, that's why I asked one stage.
No,
One stage
round rock. See, when you have supernova remnant, how will you say supernova remnant is a stage of stars, stellar remnant. You cannot say that a black body because they can't emit a new weapon. When you have, you can say when the star is in main sequence, then you can say it. Any other question?
What is P a function of?
Sorry?
What is P a function of?
Which be this function of
What is
radius, that pressure in this, see this is the radius, so pressure in this radius. Any other? Do we have time? How much? 5 minutes. Any minutes?
Cut.